All right, welcome back. So part two for double integration method. So we just went through, got the we went through the first double integration. So let's go ahead and do that for m2 of x now, m2x2, which is, again, I want to start with this moment curvature relationship. I'm not going to maybe write it out so explicitly this time. D squared v2 over dx2 squared is equal to, let's see, m2 was just minus x2 squared over 2. So this is EI times minus x2 squared over 2 kilonewton per meter. Okay, kilonewton per meter. And we just got to make sure we keep units straight later on. Okay, maybe convert this into meters, in fact, right here. Okay, maybe convert that into meters. Who knows? But that we can do that later. We got this EI business going on. That's great. So now I want to integrate once, or take the antiderivative, which is dv2 over dx2, and that is just minus x2 cubed over 6 kilonewtons per meter. And then I'm going to take one more antiderivative v2 of x, which in this case, let me call this theta. Theta 2. Theta 2 right here is minus x2 to the fourth over 24 kilonewtons per meter. And I forgot the constant, so I'll call this C3 plus C3x2 plus C4. Okay, so don't forget the constants associated with the antiderivatives. So bam, okay. And now what we have left, if this is clear to you, then you're halfway there. The next part is the boundary conditions. And so since we have 4 constants, that means we need 4 boundary conditions to solve this problem, or to finish this, to get the moment function. So 4 constants, 4 boundary conditions. So we got to go back and look at the structure here. So we have a cantilever beam that's fixed on one end. Okay, so it's fixed on one end. So let's see. So some boundary conditions. This is step 4, part 4 of this problem, part 4. BCs. So we got to identify these boundary conditions. So it's simple. The first ones are simple, right? At the support right here, at x1 equal to 0, the vertical deflection of a fixed point is 0. Okay, of a v1 is equal to 0, or you could say v1 of 0 equals 0, whatever. Okay, and then same thing here. You can say theta 1 at 0 is equal to 0. So here, really, what it looks like is this: v1 of 0 equals 0, theta 1 of 0 equals 0, right? These functions are incomplete without writing something like x1 in here, like x1, and here there would be x2 and x2, and same thing right here. There'd be an x1 like that. Okay, all that business, but it's anyway. That's neither here nor there. That should be that should be pretty straightforward to you. Theta 1 of x1, right there, like that. All right, so that's not too bad. So here so we have 2 boundary conditions. Yay. Okay. Now at x2, the boundary conditions at x2, for x2, shoot, we have, we can't look at this beam over here and say, gosh, there's anything that really stands out. The only thing that you have is the interaction between the moment function at 1 and the moment function of 2. Okay, so you have a moment function for 2 here, and what you have is that because the deflected shape has to be continuous. You can't have like some step or something, right? It has to be continuous. So whatever the deflection or slope is on this side of point B, it has to be the same as just on the other side of point B. Okay, it has to be continuous. So what does that mean? That means that at x1 equal to 5 meters, or x2 equal to 5 meters, that you have v1 equals v2. Okay, so what that means is v1 of 5 is equal to v2 of 5 meters. Okay, that's great. That's one other boundary condition. And the other is that the slopes should be the same there. Okay, now check this out. This is where everyone gets messed up. Here is that the slope theta 1, okay, right here, if I could visualize my deflected shape, here's what my deflected shape looks like. I know this drawing is getting really sloppy, but my deflected shape looks like let me draw it down here. My deflected shape here. Here's my cantilever, like this. Here's my fixed shape right here. And here are some distributed load going across like that. Okay. And my deflected shape looks, it's going to have 0 slope and 0 deflection here. And then it just kind of, you know, curves down like this. Okay. And I've totally exaggerated it, but this is what it looks like. And what I want is that the deflection at this point, at point B, is the same just to the left of point B and just to the right of point B. And we can keep this the way it is because we said V1 is upwards, V2 is upwards. So really it's like saying negative, you know, the value of V1 here is equal to the value of V2. But in terms of slope here, okay, in terms of slope, we had, you know, x1 going like this right here and x2 going like this right here. The slope in the x1 coordinate system, this is a negative slope. So this is like negative theta 1 x1, or negative theta 1 of 5 meters is equal to, but for x2, in the x2 direction, this is a positive slope. This is plus theta 2 at 5 meters. Okay, and what happens a lot is people forget this negative sign and make all kinds of mistakes because of the stinking coordinate system, right? Damn you, Cartesian. Is that a last name? Shit, I hope that's the last name. Anyway, all right, so Cartesian. Damn you, Cartesian, or Cartesia. Maybe it's a place where coordinate systems are difficult. Anyway, all right. All right, it's not that funny. Calm down, dude. All right, so here, all right. So here we have our 4 boundary conditions. Now we can plug and chug and solve for these stinking constants. So let's go through, you know, do some quick examples of this. So let's start with the first one. Let's start with the slope at 0 equals 0. So here, theta 1 at 0 is equal to, let's see, if I plug in 0 for theta 1, which was over here, I would get 0 minus 0, 0 minus 0 plus C1 equals 0. So that, therefore, C1 equals 0. Yay! And then V1 at 0, let's see here. Let's see, V1 over here, right here. So if I plug in zeros here for V1 right here, I would get 0, that would be 0, 0, 0, 0. So here it'd be 0, I don't know, gosh, I'm being too anal about this, minus 0 plus C2 is equal to 0. Therefore, C2 equals 0. Those are my most favorite constants in the whole wide world, right?